So today we're going to consider thinking about flow in multiple dimensions. And so we've gone over the Laplace equation. We've thought about flow at least and beginning to think about it at least in two dimensions and isotropic and homogeneous systems. But we're going to want to take a step and think about what does it mean as our systems are changing. But as we begin to think about that flow in three dimensions, we can first just think about it under its simplest conditions. So when we think about flow in multiple directions, we can think about it in terms of two components. We can think about it in terms of its magnitude and its direction. So we can begin to understand the magnitude of any given vector, and that vector might be the volumetric flux or that little q or velocity in any of these differing directions, right? And when we begin to think about it, our vector at any given point, let's say from 0, 0 to point A1, A2, is just going to be the square root of each of those points in the x and the y direction squared themselves, right? So it's the sum of those the square root of the sum of those squared. Now, conversely, we can think about the angle, right, which is going to be the direction, and then can think of that as the arctan of the point A in the y direction, so A2 compared to A1 in this environment. So when we denote volumetric flux in two dimensions, right, the vector of Q of volumetric flux, we can put a line over the Q and we can say it's of Q, X, and Y, or we can say it's in three dimensions, Q, X, Y, and Z. And so if we want to understand what the actual magnitude of flux in three dimensions is, we can take the square root of each of the fluxes in the x, y, and z direction squared, the sum of those. So the square root of the sum of each of the fluxes squared themselves. So when we think about it and on the top, we are thinking about an isotropic system that is homogeneous here. You know, this is essentially thinking about the Laplace equation and how we would solve for the vector of that flux in the x, y, and z directions, right? So it's the change in head over the change in a distance multiplied by a hydraulic conductivity. Now, it's possible to denote this in multiple ways. So you may see it written in this manner. You may also see that this gradient here becomes the gradient of h, or you may see it determined by an upside down triangle and h, also indicating gradient, right? So here's another symbol we can use for gradient. So each of these equations means exactly the same thing. Now, when we begin to think about what this means in an anisotropic system, remember the idea that anisotropic systems mean that water flows preferentially in one direction versus another. And that water flow, that preferential water flow in this instance is the ability of the material, that conductivity of the material to move in the X, Y, or Z direction. So again, we still have a homogeneous system here, but we have it in an anisotropic hydraulic conductivity. So our goal today a bit is just to be able to identify when we are in different conditions and to be able to also write them out. So to be able to write out different forms of hydraulic conductivity in of Darcy's law in multiple different directions, so three dimensions, and thinking about the different factors that may be influencing that those fluxes. So I just wanted to bring us back to this idea of the difference between isotropy and anisotropy, and the difference between homogeneity and heterogeneity. So if we look at the two top boxes, what we see is that as we move in space, the material itself is changing, right? So we're moving between different layers or different pockets of a material, right? So we are changing in space. Where conversely, we can have an isotropic system, meaning that water in either the X or the Y here has the ability to flow. So its hydraulic conductivity is the same in the X or Y direction, or an anisotropic system, which allows for preferential flow because we have an ability to conduct water better in the X than, let's say, the Y direction in this case. So therefore, we have a difference in our hydraulic conductivities. But where we move in space is important in heterogeneous systems. Where in homogeneous systems, no matter where we move in space, we're going to have conditions that can be anisotropic or isotropic too. So here we have a homogeneous isotropic case, right? Everything is exactly the same everywhere, and our hydraulic conductivity in the X and the Y directions are the same. And so we can think about this as our simplest form of the Laplace equation, essentially. Now, or conversely, we can have a homogeneous case, so it's the same material everywhere, but it does have differences in the hydraulic conductivity in the varying directions as a result of these factors in the system. So let's go back to that first equation that we began to think about when it came to the steady state conditions. So we have a steady state homogeneous isotropic condition. So the first component of that statement, steady state, means that over here, right, we are not, our net change in this system is going to be zero, right? So we're not, our net variation in the system is always going to be back to the same, which is zero. So that is our steady state condition. Our homogeneous condition means that no matter where we move in the X, the Y, and the Z direction, right, our system is the same in terms of the distribution of the material, right? So you're all within the same shale, or you're all within the same sand. But our hydraulic conductivity is isotropic because the way that material is oriented, our K in the X and the K in the Y and the K in the Z are all exactly the same, right? So that's what's making it isotropic. And so because that K is the same, we could divide K out here, and we could divide 0 by K, which would just be 0, and we end up with the equation that we have below. So then we can start to think about another condition, right? And again, we're trying to be able to read these equations off so we understand what's taking place. So in this system, we have a steady state condition, right? So there's no change in our system when we move around in it. It's that the head levels will remain the same in their physical positions that they're located in. And we are also in a system that's isotropic. So our hydraulic conductivity is the same everywhere, right? So we're in that kind of different space when we were thinking about it. We'll go back and we'll say, okay, where were we isotropic but heterogeneous? And we'll go take a look at that case. But here in space, we are different, right? Here in space, we have variability that we have to account for. So let's go back and take a look really quick at what we might imagine that to look like. So in this instance, the case here is, if we come back, heterogeneous, right? But isotropic. Everything's the same, but you can see that this isn't the same material everywhere, right? There's a variability that's taking place, but it's not influencing necessarily the differences in our hydrologic conductivity or hydraulic conductivity in the X or Y direction. Now, we can also talk about a system that is steady state, right? So a steady state equation, we're always starting with no change that's taking place in the system. And we can have it be homogeneous. So now in X and Y and Z, we don't need to worry about the variability that's happening in the system. But we do have changes in the hydraulic conductivity in those directions. So preferential ability to conduct potentially in the X in comparison to ability to conduct in the Y. So let's go back a couple slides and take a look at what that case is. So if we look back here, right? So now we are in a system where we're anisotropic, but we're homogeneous. So again, that idea of potentially a fractured shale system may be something that we're thinking of, or a fractured granite system. So same material everywhere we're moving within the system, but that preferential degree of flow in the system. So then finally, when we begin to think about these environments, we've now done homogeneous or heterogeneous, isotropic or anisotropic. Our final one that we're going to have is going to be this idea again of steady state. Here we are at 0 again, this time anisotropic, right? So we have a hydraulic conductivity value that's dependent upon kind of the direction of which water can be conducted, right? So how it is conducted in the X direction, how it is conducted in the Y direction, and how it is conducted in the Z direction. And we have changes in the system, right? As we move in the X, the Y, and the Z direction in terms of our material properties that we have, or our material system. So once more, let's go back and be able to put this where it belongs in what we're looking at. So if we go back, again, now we're in this heterogeneous anisotropic system. So that equation would represent a steady state condition in each of these components. So what I might suggest is, as you write out each of these equations, which designate this idea of heterogeneity and anisotropy, that you go ahead and draw a small sketch next to them so that you can visualize what this actually means for flow in the subsurface and what conditions you're actually interacting with. So when we think about these equations, right, the only thing that they are saying is that changes in the X must be balanced by changes in the Y and the Z, right? Because inputs in a mass balance equation where our steady state is 0, right, inputs have to equal our outputs in these systems. And H can be calculated everywhere with knowing only a few things. So input minus output equals that change in storage over time, which we've talked about. And an aquifer's ability to store water depends on if it's confined or unconfined. And so we're going to jump a little bit more into that as we move forward in the class.